So we're going to talk about cross-sectional volume. What does that mean? Okay? So we're going to have an area, and we're going to put a shape, the base of a shape in that area. Okay. So you see here, I have the same area, and here I have semicircles laid in there.
That's supposed to be 7.2C. I don't know if
Yes, it's
okay, I was just checking.
Brady.
Yes, we're back. We can use magic. Yes. And crayons. No, crayons are good. Crayons are better than crayons.
Okay, so back to our picture. Okay, here we have, it looks like squares laid in here. Here we have triangles laid in there. Here we have rectangles laid in there. So we are going to have to find the volume of each of these. Like imagine this, I know that they're paper, but imagine this as a solid, okay, a three-dimensional solid. All right? So it's kind of like a dome-ish thing. Okay.
Tornado.
Yeah.
A cornucopia.
Okay, but if you imagine, okay, we're going to have to find the volume of each of these infinitely thin cross-sections and do what with them?
Chop them up.
Add them together.
You have to saute.
Okay, so like an onion, okay, if you think about an onion, if we chop up an onion, we have a bunch of little semicircles, right? That fit on a circle, right? If we cut it in half, that's kind of what we're finding the volume of. Okay, we can find the volume of half an onion using this. Okay? So we're going to be working with integrals because we have to add up all of these infinitely small, infinitely thin shapes. Okay? So let's talk about how we would find the volume of one of these infinitely thin shapes. Any ideas? Like, let's talk about those squares.
You say the sum to infinity of volume of each square
Okay, how would we find the volume of a square?
by plugging the equation in as like the length of width.
Okay, the length times the width, and then what would like the thickness be? Dx or dy. Okay. So what we're working with here. Okay. Is this?
He wasn't here when we went over all the cool stuff.
Okay. So basically, we're going to sum up all of the volumes of these infinitely thin cross-sections. So if you think about like area times thickness, that is how we find volume. Well, this is area times thickness.
Dude.
Area times thickness.
Wait, so we're actually going to have a value for dx then?
No, dx or dy, that's describing the thickness. Okay? We are still going to draw a reference rectangle, and so that will tell us what our thickness is, dx or dy. Okay? And then that reference rectangle, that's where the base of our shape is going to sit. Okay? Are you ready then? So I just want to make sure that this is again. Okay. So I want to find the volume of a solid whose base is bounded by y equals x plus 1 and y equals x squared minus 1 with a cross-section of squares perpendicular to the x-axis. Okay, I'll give you a moment to write down whatever information you would like.
most of the areas you're really working at keyboard only in the first quadrant usually? Just to make it easier.
Generally, you're gonna see that. Sometimes first and second quadrant, but for the most part, yeah, the first quadrant is pretty popular. Okay, so let's draw this picture. Y equals x plus 1. Looks like that, right? Y equals x squared minus 1. So that's what we have. Okay. So I am concerned with this region in here. Okay. Now we want these cross sections to be perpendicular to the x-axis, which means when we draw in a reference rectangle, we want them to be perpendicular to the x-axis. Is that rectangle perpendicular to the x-axis?
Don't you mean squares?
No. We always draw a reference rectangle. We'll get to the squares in a little bit. Okay? What is the thickness of that rectangle? Dx. So that's telling me that our integral is going to be with respect to x. Okay? So them telling you perpendicular to the x-axis, that's important. Okay? So now, what do we do with that reference rectangle? Okay? That reference rectangle is the base for our cross-section. What is our cross-section?
Squares.
Squares. Okay? So basically, we have a square sitting there. That's popping out of the page. Okay? So let's talk first about what is the length of that rectangle. Top minus bottom. So we have our top equation is x plus 1 minus our bottom equation is x squared minus 1. Right?
Wait, let me see S. Yeah, what's on that side?
So that's our, like, this side of our square.
Alright. Wait, where's the square?
Yeah, to imagine somebody.
Okay. Let's go ahead, let's label this as maybe base. That's the base of our shape. Okay, and every problem it's going to be the base of our shape. So this is where our square is sitting, Aaron. So if you imagine like a square is popping out right here.
Oh, okay.
Like,
Be like-
somebody had their clicker.
Yeah, it'd be like from the side.
It'd be small.
Cute.
And do the small.
Otherwise it'd be a rectangle, so just like,
Right.
yeah, I get that.
Okay.
It'll be small.
So any rectangle that I draw here, it's going to have the same height. So I know this looks long, but it's going to have that same height to make it a square. Okay, so all of these are squares popping out. Okay, thank you. Appreciate that. All right. Yes, we'll get there. Okay. So what we have is negative x squared plus x plus 2, right? That is that's our base, correct?
Wait. You're trying to find the area. Why don't you want to?
Oh, I'm not finding the area yet. This is just the length of that base.
Okay, now I'm confused, because like, wouldn't you want to just go ahead and find the area, top minus bottom, find the area of that, and then multiply?
So what this formula means over here is that you're finding the area of the square or the semicircle or whatever your cross section is. This is the area of the cross section times the thickness. So what we need to do here is we need to find the area of each one of these squares and add up all of those squares.
Okay, but here's the other thing. couldn't those squares like extend on for like forever? So like you have the back square.
Not when you're revolving, no.
Well, we're not revolving. Okay, we're not revolving. We have this region, let's go back to these pictures. Like we have a region and all of these squares are sitting in that region.
Yeah, but couldn't the squares like be stacked up higher?
It'd be a right.
Stacked up higher.
He's
As in-
talking about it going higher than the actual base thing. He's not understanding that the height of it is the same as the base.
So all of these are gonna be squares, so they can't go any higher than the base.
Okay, then how about a rectangle?
Well, for right now, we're just working with squares. Like the cross section for this example is squares.
Alright,
Okay, so let's get through this, and then I have other examples that will look at different cross sections. Okay, so any little piece here, we have a square coming out. So that is the base. So how do we find the area of a square? Okay, so the area of all of these squares is base times height or side squared, right? So what we're going to do, if that's our area, then that's what we put here in our integral.
8.1.
And what are our limits of integration?
-1 degree to 2.
So it's kind of like a 3D shape rather than like a.
Right. So instead of revolving
24.
to get a 3D shape, we're just stacking in cross sections to get a 3D shape. Okay. So all of these we could sit on a table because they're all going to be flat on the bottom.
Question. I still don't quite understand how you got the base. Because basically what you just did was you took the function 1 and subtracted it by the second base. And that's supposed to give you your area.
Nope, that's not the area.
Alright, so
Top minus bottom gave us the length of this rectangle.
okay.
Okay. Then I took that, and that's also going to be the height of our square. So base times height would be this. That length squared. That's the area of a square,
Okay.
right? And so now I put the area of the square into our integral times the thickness, and we're going to add all of those up.
Alright.
Okay? Okay. Now we're going to use the same region.
So when we use rectangles, it would be straight.
Right. Okay. So some of it, Zach was kind of worried about rectangles. Well, how do you know how high the rectangle is going to go? They will either tell you the height of the rectangle, like a rectangle with height 3, or in this case, rectangles whose height is twice the base. Okay. So we have the same region. We still have cross sections perpendicular to the x-axis. Okay.
So are we only using dx in these examples? Or on this?
No. Oh, we'll get to a dy example.
What's the difference? Because if you're not rotating it, then you just.
If I say that your cross sections are perpendicular to the y-axis, that would make our rectangles.
Would you use the left one strike rule? Or right one?
Yes. Okay. So let's talk about the base. The base for these cross sections is still going to be top minus bottom, right? So a reference rectangle has thickness dx, and so that's what we're integrating with respect to. Let's talk about the area of these rectangles. Okay, how do we find the area of a rectangle? Base times height. Well, we just figured out that the base is top minus bottom times the height of our rectangle. Our rectangle has a height that is twice the base. So how would we describe that? 2 times negative x squared plus x plus 2. Okay? So our integral that goes from -1 to 2, we're going to put in the area of these rectangles. So I would write 2 times negative x squared plus x plus 2 quantity squared. Easier to throw in there.
Why is it squared again?
Well, because you just multiply those.
This times this is basically that squared. I have negative x squared plus x plus 2 times negative x squared plus x plus 2. So you can write it all out like that, Aaron. Or I like 2 times 2 is the same thing as 2 squared. That's just all I did. Because I have this times itself. Okay, we got it. Josh.
Just as a quick observation, couldn't you just taking the answer of the previous one and just doubled it?
Yes. However, I want to see this set up. Okay. So this is what I want to see when you do these problems. I want to see your picture. I want to see your reference rectangle. I want to see what your base is, and then I want to see your area. Okay. Then you can find the volume.
If we're doing the same cross, like if we're doing different cross sections for the same graph, do we have to redraw the graph?
No. Did anybody plug this into their calculator?
Yeah, it's 81 bits.
It's 9.
That wasn't.
It's not 9.
What the heck, bro? I trust you.
That should be
Let me see.
Forgot to square this.
It should be doubled.
Okay, same region. Now our cross sections are semicircle. Do you?
I'm good at that.
Okay, so we still have cross sections that are perpendicular to the x-axis. So we still have integrals with respect to x. Therefore, we're still going from -1 to 2. Now, Carter, what did you just say?
1/2 pi squared.
Okay, we find the area of a semicircle by taking 1/2 pi r squared. Hold on.
So elementary right now.
You got it. Hang on. Okay. So let's talk about this base. We already know that this base is negative x squared plus x plus 2. Okay, top minus bottom. That's the base of our semicircle now. Okay, Brady. What does that represent in terms of our semicircle?
Diameter.
Very good. So if I want 1/2 pi r squared, what are we going to have to do with that? Okay. So the area of our semicircle is 1/2 times pi times radius squared. Well, it's actually the diameter divided by 2. So since these are semicircles, it represents the diameter. And so we have to cut it in half for our radius. So based on that, what we can do is we could write 1/8 pi times negative x squared plus x plus 2. Or you can write it like that. It doesn't matter. But if it's easier to plug in your calculator like this, which it probably is, okay, you can rewrite it.
Isn't the negative x squared plus x squared?
Oh, I forgot my square. I think I said it. Sorry. Where did I get the extra?
We squared the two.
Okay, that 2 is being squared, so it's 1/2 times 1/4
So
essentially.
with this one, if you want, you have to leave the decimal.
This you can integrate without the pi and then put it in, if you want to.
And then put the pi in.
Mhm.
Well, the pi at the end.
Right, because
It's a constant.
constants can be thrown out here, right? So you can integrate this and then multiply it by 1/8 pi if you want to.
I got 81 pi over 8.
81 pi over 8?
AD.
Oh, over 8. Do you agree?
I got I focus on the band.
I got one.
You did not. Why are you getting your... Wait, what are you doing?
Are we doing our Zoom?
Aaron, I don't need your help.
Yes.
I don't need your help either. Is 81 pi over 80, is anyone else getting that? Okay, thank
The
you.
next one, equal that over triangles.
I don't know. I can't remember.
That's skating.
They're obtuse.
This is any triangle, actually.
We don't got one.
This, yes.
So for like, something like this, why is it like, I don't know, I got.
Well, because this represents a diameter in a circle, and so we had to cut it in half to be our radius. So this is radius squared.
Alright.
Does that make sense?
So just divided by 2 is the radius.
Okay, so here's our region. But I want cross sections perpendicular to the y-axis.
So it's right to left, Nate.
Hi, Jimmy. Nice job.
So these have thickness dy. Which means, what are we going to have to do with our equations? Okay, so we have y equals 2 radical x.
Y divided by 2 squared.
So x is y squared over 4. Is that what you said?
Yeah.
Wait a second, why do we need to move to D1?
Because we have cross sections perpendicular to the y-axis.
Oh, I didn't see.
Okay, and do you see my reference rectangle?
Yeah.
Okay.
I just didn't see it perfectly.
Okay, perfect. So first of all, let's talk about the base. How long is the base of this cross section? Right minus left. So y squared over 4 minus 0. So that's our base. Okay. Let's talk about the area of rectangles whose height is 3 times the length of the base. So our area would be base times
3 times.
Jimmy, what's our height? You were saying it.
Oh, 3 times our base. Which is just 3 times the base squared.
Okay. So our integral. Carly, what are our limits?
Oh.
Okay. Carly, what are our limits of integration?
0 to 6.
Very good. 0 to 6. I'm going to rewrite this as 3 over 16 y to the 4th.
Oh, okay.
This is what we do by hand, because
No, we're not doing
no, I
This would be a non-calculated problem.
Wait, what about the halfway integrate 3 over
What?
isn't it 1/2 base times height?
No, because we're talking about rectangles.
Oh,
I lied about triangle. We're using a
Because he
triangle.
said triangle with that word.
Okay, let's talk about triangles though. So you could have one of two things. They could tell you that you have isosceles triangles whose
Base is 12.
right, so like the height is something compared to the base, or the height is 3. Or they could say they are equilateral triangles.
Which is a geometry.
Okay, let's talk about equilateral triangles real quickly. If this is our base, how do we figure out our height?
Base by no, it's just two.
Base times height divided by 2. Or no.
That's how you find the area. But if you have an equilateral triangle, how do you know what the height is what I'm asking.
Be radical 3.
So this is
base
a
of
60-degree angle, right?
Be radical 3 base of 2.
Oh,
Make the
it's
base by
the proportion you don't want to talk about. No?
Mm-hmm.
Radical-
So-
radical 3 base.
So since this, all of this is base, in this right triangle, this is 1/2 base, which means to go from my short leg to my long leg, we multiply by radical 3. Okay. So if you have an equilateral triangle, that little tidbit of geometry may be helpful.
We want some AP.
Oh.
Oh, geez.
Okay,
Even did that AP geometry.
What is this?
that is.
I'm leaving.
So take it out the door. Before I will let you start on your assignment, what I'm going to do is give you a sticky note
We're here forever.
for you to do this problem on.
Sticking out. Yeah, for real.
All I want you to do is set it up. What? All I care about is the setup. I know that you can evaluate an integral, okay? I'll let you practice that in your homework. I want you to set it up. I'm hoping that you don't have to graph this on your calculator.
Yeah, I forgot what it looked like.
Yeah,
Do we need to do